Yes, hello everyone. Thanks for being here, and yeah, welcome to the workshop. So the title is Bridging the Gap Between NISQ and Fault-Tolerant Quantum Computing. And yeah, basically this workshop is kind of a spin-off from the long program that we had here at IPAM, that most of us were participants here. So that was back in 2023. So quickly, as we were participating in the workshop, it kind of became quite evident this disconnect between the scientific communities, between NISQ and fault tolerance, and this is how we thought about this workshop to try and bridge this gap and see how researchers can start communicating more to each other about this. Yes, and also the speakers have already received these discussion questions. The participants have not received them, but feel free to take a photo. And the idea is to try and motivate the speakers to discuss a little bit about this. So kind of in a high level, just a high level discussion about their insights about these questions. So I will also during my talk discuss about this, so kind of all of them. So for the speakers, at least one will be good. Yeah, so starting, we'll kind of discuss the first question and smoothly transition into the main topic of my talk. So yeah, around these two distinct quantum computing regimes. So we have NISQ, noise intermeter scale quantum, and fault tolerance. And in NISQ, we mainly have hybrid quantum classical algorithms. And we have pretty kind of relatively small number of physical qubits. And in terms of error suppression, we have quantum error mitigation. While for fault tolerance, things are pretty different there. So I say here it comes with a great complexity. So kind of, whereas its complexity is that we have all these different layers of computation that have to work together to do what it's supposed to be done. So we need also expertise from many different areas of research. So to give a more detailed breakdown of this, so the way I see it, we have 4 key layers, which is the quantum algorithms, which results in a detailed breakdown of the circuit operation needed. Then we have the logical quantum processor layer, which basically perform the compilation to lay out these operations in an efficient way. Then the error suppression. And finally, we have the physical quantum processor layer, where we need to make assumptions, specific assumptions of the hardware that we are using to run the computation. And so the way I see it is fault tolerance was always the end goal of quantum computation. But as we're trying to get there, we have smaller devices that will are becoming and will keep becoming available. And then kind of the idea behind NISQ is, okay, can we do something with them? So when the term was introduced back in 2016, I was actually still in my Bachelor of Physics, so I was not following very closely the research outputs. But when I started my PhD, there was still a lot of excitement about NISQ. And I feel like now more excitement is towards fault tolerance. And but this also says how far we have come, because back in 2016, we start being it seems we had more information about NISQ devices, but now it seems hardware providers provide a specific timeline of when they will deliver these fault tolerance devices, which is something that we did not have back in 2016. And in terms of expectations, I think this says as well that we are heading to fault tolerance, kind of full speed. And I think it's pretty exciting because the algorithms and essentially the applications we can target seems to be more impactful. So I think there's a lot of excitement around building these devices and also finding applications that will provide something meaningful. And the next question is, how can we bridge this gap? And back 1-2 years ago, we had this work on early fault-tolerant quantum computing, which is we saw it as a way to bridge this gap. And the idea is to kind of move away from this disconnect. And in this work, we mostly focus between early fault tolerance and fault tolerance, like this connection here. And the main way we approach this is from quantum algorithms perspective, and we try to analyze these two regimes, where one of the main differences is that we had some limited ability to achieve fault tolerance in terms of scaling. So the main conclusions of this is that we kind of assumed the same quantum resources between early fault tolerance in the sense of number of physical qubits and the error correction model used. But then with algorithms from early fault tolerance, what we saw is we were able to target a larger number of logical qubits. So more interesting problems. Yeah.
Scalability access, is that the number of logical qubits?
No, the scalability access it's characterizing the ability of the device to error correction. So it's kind of a noise model on high level. Yes, and transitioning now to the main topic of my talk, which is achieving utility scale applications through full stack code design of fault tolerance. The idea here is to again try to assess the performance of fault tolerance quantum computing by taking into account all the layers of computation. So this is where the full stack comes into play, and the code design comes into play from the hardware aspect, where we make some specific assumptions about the hardware. Yeah, but before going into this, I want to discuss a little bit about the application. So it seems that there is more and more interest going on around the quest for quantum applications. So I cite one paper here, which is the Grand Challenge of Quantum Applications from Google, but there are a lot of many more papers coming up trying to understand and explore ideas around quantum applications for fault tolerance. And I think also this competition, the X-Prize Quantum Application competition, is a testimony to the interest around quantum applications that's going on now. And I also find this work very interesting, and we also have Michael here. So what I like a lot about this work is that it was kind of one of the first to choose specific problems and try to map them to two key metrics, like the number of physical qubits and the runtime for different hardware platforms. And I think what is interesting here is that in order to get these numbers, these two key metrics, one really needs quantum resource estimation analysis. So yeah, here I want to highlight why it's interesting to perform quantum resource estimations and try to make them more and more accurate and reliable. So the first thing is that we have different applications going on, and then we can map these applications to specific hardware key metrics like the physical qubit and the runtime, which essentially tell us the size of the quantum compute. For example, the physical qubits, we see that's the size of the quantum computer that we need. And through this methodology, we can also explore different advances, see how different advances in the field affect these key metrics. And also it can help in the co-design of fault-tolerant quantum computer architectures, so we can take different assumptions on the hardware level and see how it could perform in practice. So essentially this could also save a lot of time from in the lab of seeing how things could play out. And through this whole process, we can really identify utility scale applications in the sense that we can get some understanding on the runtime, and then we can start benchmarking with classical algorithms and see where we could really provide something new from quantum. And yeah, so seeing in more detail what was going on in this work, one thing that it was interesting to me is that for ion trap type of systems, the runtime was pretty high. And it seemed to me as well that the hardware always get a lot of focus in terms of how to make things become a reality, but the motivation behind this work as well is that hardware is one of the layers out of these four key layers, and how can advances in the other layers support the hardware to get it where it needs to be. Yeah. So going now into more details about the specific application that we are using in this work. So this is the CO2 utilization for green energy, and the key, like the high-level idea here is that we know that there is this chemical reaction where we have CO2 and hydrogen, and with like certain catalyst, it can be mapped to renewable fuels and raw materials. And this is pretty interesting because like we have here a nice schematic from a paper. It's cited here at the end. And like the reduction or even removal of CO2 from the atmosphere is like a pretty important problem. And like there are a lot of different methods one could approach this. So basically the one I'm discussing here is this like fuels from CO2. And if the hydrogen comes from like green sources, like green hydrogen, then the whole process becomes green, which is even more interesting. And so we know like that we have this high-level path here, so it more details like methanol and water. But then the problem behind this is that this RU-bait catalyst and then this whole reaction like has a lot of intermediate steps. So this is like one of the intermediate reactions going on. So here. And the problem is that in order to study this problem, we need to be able essentially to calculate this relative electronic energy, which basically means we need to calculate the electronic energies of the systems involved. And in this work, we studied this system here, the catalyst, as like a proxy of how this like application could play out. And again, like why is this interesting and why do we want to do that? It's essentially because these electronic energies eventually go into these reaction rates. And then this is kind of the information that we need in order to understand like the temperature dependence of the reaction, the rate determining step, like how can we optimize to make it faster, and also like in general catalyst optimization to make it more perform better. And the problem is that this energy calculation from classical methods seems to be pretty challenging. So here we have different classical methods and then the relative electronic energy. And we see that different methods deviate quite a lot. And then we have these two that are kind of pretty close. So this is also from our work. But eventually what we need is like to be within chemical accuracy. So it means that these methods need to be within this yellow bar to be kind of in accordance. And the problem is that we really need to be accurate about this estimation because this goes to the exponential. So it really matters at the end for understanding what comes next. So even like qualitatively, it's important. Yes, so I think another challenge general for quantum applications is that, so here I have like the quantum benchmarking graph where I have like the application I'm discussing with like different, like kind of as a workflow with different steps. And I think in general, another challenge for quantum applications is that they're not going to replace the whole workflow of a specific application. But instead, it's going to be like a very specific step that is kind of challenging. So for example, like here's what this schematic wants to give us a message that like the quantum computation will be a part of the whole like workflow. And I think this is pretty challenging for like in general like quantum applications because it means we really just need to understand where this bottleneck comes and why and how it will be like impactful. So like can quantum computers help? So this is kind of the main result of our work with Matt. So the idea is we followed the steps from like Michael's work and tried to incorporate like different advances, different layers of the computation to try and see where we are today. So I'm going to discuss like in more details about the different assumptions that we did in each layer. But before we go there, I kind of want to show the predicted runtime quantum advantage that we have. So this is the runtime for the classical, and then the runtime for the quantum. So we assume like two different hardware, ion trap and neutral atoms. And if we also take into account the overlap, which is pretty important for quantum algorithms, the runtimes remain pretty much the same for this specific application. And I also think like an important thing here, is that for classical algorithms, we see we have this exponential increase in the runtime as we increase the system size. So this is for the same catalyst system, but now we have more orbitals. And while for the quantum, we have like a linear scaling. And then in the question about the different definitions of quantum advantage, I think it will be pretty interesting if we like agree to some key metrics, and then I think for like research papers, it will become easier to compare between different developments to see where we are. Yeah.
To me, this left-hand side seems like pretty optimistic for CPU runtimes, right? So even at like 60 orbitals, quantum computers are still beating out the classical computers on this. Do you know when that crossover likely would be on this graph, or where the CPU becomes better than the quantum computer?
Yeah, I think this is like around 50 orbitals is where we start like seeing the like if we go below 50 orbitals, I think CPU will start becoming faster.
Oh, really? Okay, that's a pretty precipitous drop from the 60. Cool. Thank you.
Yeah, maybe I can add an important note is that this is total process time.
Yeah, right.
So that it's so I can run in parallel on 1 million cores.
Yeah.
Right,
Okay.
and so this is a good question about what is quantum advantage. Here, there's a demonstration of total integrated process time, right? And so you could run your QPUs in parallel as well. There's sampling, so you can just use sampling. You've got to take M shots or something, so just use M quantum computers. So there's a naive parallelism of maybe 1,000 to 1 million you could get if you could pay for 1 million quantum computers. On the classical side, we have big, large, scalable classical supercomputers with 1 million cores.
Yes.
And so both of those can be divided by some factor. But we didn't divide them because so it's the integrated runtime.
Okay, cool. Thank you.
Here is another assumption that all these orbitals, they actually pose the difficulty, right? So you do compute full configuration interaction in a sense, right? And there are systems with 60 or even 100 or 200 orbitals, which can be treated classically in perturbative regime because not all these orbitals are so that difficult to solve.
I think Nicole is going to discuss more about this, like with chemical, in the next topic. But yeah,
I assume that's like referring to like active space.
Yeah.
So do you include the classical time in this as well, and the quantum time, and the setup time it takes to generate the problem and everything?
Yeah. So basically, as Matt was saying, like this classical time here is like the whole clock time multiplied by the nodes used. So if we just take, like, we assume we can run, like, so basically this definition of runtime comes from like a Google paper. That's how they were like comparing. So we try to like use the same. So this goes back in the discussion about the different definitions and how we can compare.
Well, I was talking about the quantum time.
Okay,
the
sorry.
classical time associated with setting up the quantum problem.
No, so this is just for the just for the energy estimation. So we don't include, because we assume we have, so basically we assume we have exactly the same problem as an input and we want to compute the energy. So like the preparation is the same for both, because like both the classical and the quantum we need to prepare the system. So.
And do you do analysis for superconducting qubits too? Because that would be better.
Yeah, I'm going to discuss more about this again.
This quantum chemistry algorithms, they're not parallelizable. So how does it matter how many cores you use?
Sorry, what's not
The
parallelizable?
quantum chemistry algorithms, basically.
My quantum chemistry algorithm is parallelizable.
Which one?
The selected CI, you just diagonalize a matrix and you ask a big classical computer to run in parallel on 100 nodes or 1,000 nodes to do sparse matrix diagonalization in parallel.
See.
I always thought it was unfair to multiply times the number of cores though, because a CPU is a box, right? So you buy this box, it has whatever in it.
Yeah,
You should just treat it as a box.
it is a great question that I don't know the answer to, and I think that's
Yeah, I saw that in that paper, and I always had a problem with that paper because of that.
So maybe to follow on that, right? Like this is total integrated time. How long does it take in wall time?
So I don't remember the times, but if we just take the walk time, I think like runtime kind of advantage is like the predictor runtime is challenged. So I think it really drops.
So the actual runtime's like 8 hours for the
Yeah.
classical. Okay. So it's a you know, the classical point is an actual run that I actually ran on a real computer. So that's an observed point with all the inefficiencies of my code not being perfectly parallelizable. The quantum could also be run in parallel with no efficiency, with no like MPI latency overhead just by sampling on different processors.
Just curious.
Yeah.
Yeah.
Thanks. So I look at the plot on the left, from my understanding, right, that means that we're only seeing maybe a gap of 20x speed up, right? I unfortunately also was maligned with having an econ undergraduate degree too. So a 20x speed up, right, does that really justify the cost of a quantum computer then? Like, should we be thinking about actually further along the right on that axis, like increasing n to 200 or more?
Yeah, so this is another like good question about like the cost of the quantum computer versus the classical, which we already have this doesn't really cost much. But then, like if we go back to the way I see it, if we go back to like the definition of the problem is that we already have the classical devices, like the classical compute, and we already have this problem here, but we don't have a like large-scale solution. We don't have like industrial plants making this. So, you know, it seems that it's kind of a real problem, and we really cannot fully understand what it needs to make it a reality. So I think, you know, if it justifies the cost and like the dollar, you know, then it goes back again to this, that the quantum application is going to be a part of this, and, you know, building the quantum computers takes a lot of money, and, you know, the question of the impact and in terms of like, if we're going to get this money back or if we're going to solve like a really important problem and we don't care about the money because we have like green energy, which is like great, so it's kind of priceless, then, you know, it's kind of interesting question, I think.
So just to understand better, so that means that you're saying that we should be thinking about this from two dimensions, right? A time dimension, but also a qualitative accuracy dimension. And you're saying that when we evaluate the performance of our quantum computers, the time dimension is not really where we're winning on, right? We have to be having a qualitative or like a significant improvement in accuracy to justify this.
Mm-hmm.
And then do we also, what's the, maybe this is outside of the scope, but what's the justification for why we would believe that there's this qualitative improvement?
So Nicole is pointing to herself, so I think
We'll talk about this in the next
going to
Very
discuss.
good.
Let's have this discussion next.
But just in one sentence, go to the next slide. The classical algorithm isn't guaranteed to be accurate. The quantum algorithm is guaranteed to be accurate. So the classical algorithm can be pushed to arbitrary accuracy with infinite resources. But you know, we did a run here which got to some accuracy, which we talked about more in the paper. The quantum computer gives you a certificate. It says, I guarantee up to our ability to do math, I guarantee that this is accurate.
Well, but would we need to use pre-born Oppenheimer approximations though if we wanted it to be truly certificate?
No, it's a certificate within the model. The
Yeah,
model,
so
the
that,
model
exactly.
is
That,
important.
again, that's the same thing. Let's let her continue, right? But I think that argument also has.
Yeah, so to this point in terms of like accuracy, I don't have the plot here, but in the paper we also have a plot of like runtime it takes for the quantum computation versus like accuracy for the 56 orbital. So we can, so compared to classical, it was hard to tune this chemical accuracy to what we wanted. Like for quantum, we can really like say we want this accuracy and we can get the runtime. Yeah, so I don't have it here. Yeah, Nicole is going to discuss right after more about this. But to be honest, I think it's great. Like I didn't expect this engagement in my talk, so I enjoyed it pretty much. Yeah, so going like next, I'm going to quickly go through the rest of the things now. So in terms of like what we included in different layers of computation. So for the quantum algorithm, we use this spectral amplification and double factorized tensor hyperconduction quantum algorithm, which is a recent work from Google. And we get the circuits in PyLictor, and these are proxy circuits. So basically what we do is we try to match the tick gate counts between the original circuits, like what is proposed in the work, with the circuits that we have. And then comes the next layer, which is the compilation scheme. So we use BenchQ for that, which uses graph state compilation. And the main idea is that the quantum circuit can be mapped to an algorithm-specific graph state. And why is this good? Is because graph states are like a very well studied field outside of quantum computation. So it means we have a lot of optimizations and things to implement for this to work. And yeah, this is like all of the schematics here are equivalent. And basically for the graph state compilation, we have like 3 key main things, which is the graph state preparation itself, like the distillation and the T measurements. So from like the software, we can also like get a detailed breakdown of how these operations map to cycles, surface code cycles. And then the total runtime is like the surface code cycles multiplied by the cycle time for the specific hardware. And then we also use PyZX, which implements ZX calculus. And then the idea here is that the quantum circuit is simplified through the ZX algebra. And then, yeah, we have like some savings. And then the next thing is about error correction. So we look into magic state distillation and also magic state captivation. And then the key things that we need here for the simulations are these parameters, like the physical error, the logical, the number of qubits and cycles for like different distillation protocols. And from cultivation is basically the same. Go back to this newer work, and we can have like savings in both physical qubits and runtime. And then in all of these simulations, we do like time optimal. So we want to like reduce the time, and that means we don't like think too much about like this means we are okay with increasing the space. So for example, like if we see here this protocol, which is basically the magic state cultivation, like these states here is the most costly in terms of number of physical qubits. So basically, we assume that we have all of them available so that we don't have to wait because we don't have like qubits available. So that's what I mean, like we optimize for time. And finally, in terms of like the hardware, so we have we are looking into like a modular architecture. So basically, the idea is that we'll have different elementary logical units to map to specific logical qubits. So here the mapping is 1-to-1. So basically, the main idea here is that ideally we would like the whole quantum computation to be on one chip, but this is not practical. So we're going to need like many chips to some extent, like communicating to each other. So this is how you can think about this elementary logical unit. And then the assumption here is that this can support around 1,000 ions. And the next thing is how these units communicate to each other. So this is based on this work from Simon, where we have like different hardware assumptions coming into play, which I have them here. So we have, yeah, these numbers. I'm not going to mention them, but like kind of the main idea here is that we want to have the inter-ELU communication to be as fast as the inner-ELU communications. And in order to make this work, it means that we need to find the number of communication channels that can support this. So basically, at the end, this is like a small optimization problem that happens in the simulation, and it's all based to Simon's work to kind of find this number of communication ions needed. And then the next thing is that how we're going to lay out these logical units in space. And so for this, we have like two assumptions. One is this 2-row layout where each logical unit communicates like with 3, left, right, and down on top. And this is kind of the baseline. But then what it will be great and what we see a lot being discussed about with like ion type system is all-to-all connectivity. But when we have so many like physical qubits and logical, the logical level will be hard to have like all-to-all connected. So basically what we apply here is an effective all-to-all. And the idea is that if we look at our circuits, so the input circuit's around 1,000 logical qubits, and then if we look at the 2-qubit, like the distinct 2-qubit pair, so the logical level is around 150. So basically this tells us that we can imagine we could like take advantage of this and have like an effective all-to-all where we don't have like to have all the logical qubits, all of the logical units communicate to each other. So this is the other assumption, and basically what we are doing in this work, in this analysis, is that we are seeing this as kind of buttons on and off in all of these layers that I discussed, and we kind of turn them on and off and see what saving we have and what type of results we get in number of physical qubits and runtime. And yeah, looking into more detail.
Katerina, give me a second here. I'm trying to. It seems like not all of these ones and zeros have been turned on and off. Right, is that because some of these are like incompatible with one another? Like we can't go.
No, this is limitation of the simulations. For example, like the graph state, like another interesting thing here would be to have like the graph state compilation versus like the compilation scheme used in Michael's work and like others. But we don't have this implementation. So where we don't have like, that's why we don't have all of them, because like.
Very cool. This is an awesome graph, by the way. I love this.
Yeah, and then like if we look into kind of two examples of what's going on. So for example, if we see the effect of the algorithm improvement versus if we have like the close this off and we have all the other effects, it's interesting to see that the runtime is reduced more from like the other innovations compared to the algorithm. And then another interesting thing here, if you look this carefully, what it says is that the combined improvements that we get from like turning two buttons on, it's not the product of like the independent contribution. So basically this suggests that it's more complex when it works in practice, and we really need to try and improve these softwares to kind of understand what is going on. And yeah, so this is also another like way of seeing this, is like the isolated effect of the different innovations for runtime and qubits. And here I have basic and detailed. So basic goes to not having this modular architecture, while detailed is with the modular architecture. And if we see the physical qubits like between the basic hardware modeling versus the detailed, this is how it looks like. So the detailed basically increase the number of physical qubits that we need. Yeah, and then a note on the runtime is that if you remember from like the slide earlier, it was 130 years in the previous work. So this is like, and goes back to 6 days, while previously said 22 years and 1 day. This is because we assume different surface code cycle times. So we are based on Simon's work, so that's why we have this difference. Yeah, and then like quickly on other architectures. So now we have like, we also look at neutral atoms, and if we see here what's going on is we have a bit of savings in like runtime and qubits. The qubits here is like this basic hardware model, so we did not have like the detailed for the neutral atoms. And the reason for this is that we included this analysis of how erasure conversion from this work could increase the error threshold, which basically,
Finish your sentence.
which basically helps like save both on the runtime and physical qubits.
For the neutral atoms, are you working within like the digital paradigm for neutral atoms or digital analog?
I'm not sure what you mean by this.
You have digital
She's doing-
circuits for this.
Digital.
Yeah.
Digital, she's doing fault-tolerance.
Mm-hmm.
Yeah, good question about the terminology here. So what is this NS protocol and the SCC?
So SCC stands for like surface code cycle time. So this is the time to do like a full like a syndrome extraction for the specific hardware. So it depends on the hardware as well.
So what is NS protocol?
The magic state. Mm-hmm. Yeah. Yeah, and then yeah.
Actually, just one quick question on the topic of magic state. So you're only using cultivation here, right? You're not like stacking some sort of distillation on top of the cultivation?
No, it's like distillation or cultivation, in terms like.
Cool. Okay, so you're able to come up with a cultivation process which is low enough error rate that you can actually implement the full output.
Yeah, so this is like we basically like the main.
Oh, because you have 10 to the minus 4 error rate, then
Yeah.
you can achieve. Okay, with 10 to the minus 4 physical error rate, yes, then it's reasonable for cultivation to get to the error rates that are good enough for a full FTQC article.
Is that like 10 to the minus 9 on the t-states? Is that about machine?
So I think it's 10 to the minus 12, like the extrapolation that we use. So
Sorry?
So that should be achievable. I don't know what you got.
Yeah.
Yeah, so this is like for the basically for the whole like error correction implementations, we have
Wow.
like,
That's
that's
I don't remember that from the paper.
wow.
Yeah, so the thing is in the paper they didn't have like 1 to like into the minus 4, they have like 5 into the minus 4, so it's basically an extrapolation.
Ah, okay.
Yeah,
Nice. I love seeing it.
but yeah.
I did not know
Is
it was
that-
that good.
I don't know, I got the impression that wasn't possible. I don't know, that they had some doubts about that.
Yeah, I mean, this could, like, they did not have the simulations for this, so basically I just took the numbers and did like an extrapolation.
Yeah, I think the problem is that they're, well, maybe, a lot of it comes from the rejection at the beginning, right? So I don't know how much better you can
But
get.
for the larger systems, it's only like a distillation that we used for the. So this is like for the 56 orbitals, we kind of have this. But then for like the 100 and more, we just use distillation.
I mean, that'll just affect your number of qubits. Probably won't affect your time so much.
Yeah. And yeah, so quickly about like superconducting. So yeah, like this goes back to the assumptions that we did, and yeah, here is like now a different software which is like top quad from 1 qubit, and you know if you're not in favor of like neutral atoms or ion traps, or like the assumption is kind of not in favor of the assumptions used, like this is a different architecture, and then yeah, so basically different compilation scheme. And we have the same problem. And then, yeah, another interesting thing here is like we have different assumptions on. So yeah, basically I have to say that this is now a different work, which is how to build a quantum supercomputer. You can find it on arXiv. But these tables that I'm showing here are not yet incorporated in the arXiv version. Yeah, and then we can have like different assumptions about the hardware parameters here, which is captured by the desired baseline and target. So the way you could see it's like baseline could be pessimistic, target like nominal, and desired like optimistic. And you can find more details about these assumptions in the paper. And then like kind of the interesting thing here is the like predicted runtime quantum advantage. So basically the main point of classical VS quantum still holds for this application. So if you're not in favor of like the other systems, if you're in favor of this, it's still like applicable. And then if we put them all together, this is how it looks like. Yeah, just show this here. And then, yeah, so basically this brings me to kind of the end. So in a nutshell, what we did is we focused on a specific application, and we like tried to motivate why this application is interesting and kind of discuss a little bit about the impact and what to consider there. And then we kind of introduce some innovation in all of these layers of computation, which is based on previous work, and then try to see how can we benchmark quantum and classical. And kind of to quickly discuss a bit about the last two questions in terms of like transition to fault tolerance and what expertise is required from other disciplines compared to mine. So I think like kind of discuss a little bit about this, that you know there are a lot of papers getting out there about innovation in these different layers, but you know there's a lot of expertise that one needs to have to kind of understand what's going on in the full stack. So I think it would be great if you know like research like scientists keep this in mind for like the papers to kind of try to have some also high-level discussions, so that if you like live in the world of quantum error correction, then the like scientists on the compilation scheme and like on the algorithm can also understand like the high-level results, so you know can incorporate them in the work. So kind of keep this in mind, I would say. So that's kind of what I see is needed. And then in terms of what is the most open problem in the corner of quantum computing, so I think my case is the quantum applications. So I think there's a lot of interest about this, and there are a lot of things out there that could be interesting to apply to quantum computation. So it's kind of So for example, like we are at University of Wisconsin-Madison, so we have a lot of other research scientists there, so it's kind of funny. We go around with Matt, like knock doors and ask people to talk to us and say what they cannot do with the classical devices and where they struggle. So I think, like having more open doors would be great, and having more communication between researchers in the quantum world and outside will really be impactful. Yeah, so I think that's the end of my talk, and kind of take-home message is that we need all of the layers to advance in parallel to see the full potential of quantum computing, that quantum research estimation analysis can help us understand what's going on, and we really need to identify positive real-world impactful applications. Yeah, thanks.